Okay, so let's talk about the transformer. This part is very complicated, also with lots of details. I will try my best to explain many of the parts clearly for you. And if you still have any questions, I'd like to recommend you to read the papers we provide you with in the schedule spreadsheet. Because for the transformer and bird, these two models, they are very new. And normally we cannot find any textbook which can cover these kinds of models actually. We can only read the papers, proposing the transformer and bird. Then you can check the details for these models. So if you have any question for the transformers or unclear parts for the models, then you can refer to the papers we provide you in the schedule spreadsheet, and we have added links to the papers already. So for the transformer, we have three parts about safe attention, then we can come to the encoder by utilizing the smart head safe attention, and then we can further build a deep transformer model by stacking multiple encoders on top of each other. So in the very beginning, we can illustrate the architecture of the transformer first. Inside you can see, we have multiple layers. And in the vanilla transformer, this architecture is in the shape of the autoencoder, very similar to autoencoder. We have encoders, we have decoders. Given an input, like in one language, right? In one language, via the encoders, and we can compress the input into some concise embedding vectors, which can be further fed as input for the decoders, and we can generate the results as a translation, right? So it is in the same shape as the autoencoders with the encoder part or the decoder part. So by utilizing this transformer, we can do many tasks. Like we can do the translation of one language to another one, as shown here. So the name transform actually is very interesting. So nowadays in deep learning, the researchers like to use the name from some other areas like animation movies as a name for their models. It's very common actually. So don't be confused by the name transformer. Actually, it is the name for the model we are discussing here, not this guy anymore. Okay, so in the following part, we can illustrate the more detailed information for the encoders and decoders for you. So here, if we take one single layer of the encoder and decoder out, and what its internal architecture will be like. If we take out one layer of encoder or one layer of the decoder out, and we illustrate the architecture in this page. In both the encoder and decoder, the architecture is very similar. It contains the attention layer together with the feed-forward layer. This feed-forward layer is very similar to the multi-layer perception with one single layer, as shown here. Right? We can just think this one as a multi-layer perception. How about this attention? This attention is very special. It is called safe attention. In other words, we calculate the attention scores purely based on the inputs, with nothing to do about these outputs at all. So we calculate the attention score among the different inputs, then we can assign different weights to different inputs, for learning their representations. We can discuss this later. This is for the encoder. The decoder is very similar. We also have this feed-forward layer, also with a safe attention layer. And the main difference here lies in the encoder-decoder attention layer. This is also the safe attention actually. However, here we assign them with a different name instead. The main reason we have this actual attention layer, the main reason is because we have to feed this result from this encoder as input for decoder. This one we receive input from this one, right? Because we have to provide this encoding results for the decoder part, right? And this one we receive input from the encoders. At the same time, this decoder will also receive input from the raw inputs. We can illustrate this one later. Why is a decoder will receive two inputs from both the encoder or some other extra raw inputs? We can show you later. So right now, you just need to know, inside both the encoder and decoder, we have two layers: the feed-forward layer, also the attention layer. It should be enough right now. So let's take this encoder out, and we can first look at its internal architecture again. We mentioned this one we have is the two layers, attention layer, and also the feed-forward layer, and how to use the layers for learning the representation for the inputs. And we can take this layer of this encoder out, and we also feed this layer with some inputs. Let's assume we have some sentence input of some words, which will be one sentence, right, with three words as shown here. So given the words, also according to the vocabulary set of this language, we can provide this raw vector representation of each word in this sentence, right? Each one will be represented as a vector like x1, x2, x3. This vector can be like one hot coding of this word in this language in the vocabulary set, right? So according to the raw inputs like x1, x2, x3, and then this encoder will compress these inputs into some concise vector representations like z1, z2, z3. Then you may wonder, how can we calculate this z1, z2, z3 based on these inputs as shown here? We learn this z1, z2, z3 based on the safe attention. This is a mechanism. So according to the inputs, we can assign different inputs with different weights for calculating the Z1, Z2, Z3. We mentioned that this order doesn't matter anymore in this kind of language, right? So therefore, inside the transformer, we just discard these orders. We fit these three as independent inputs. And in the following part, we will illustrate how to calculate Z1, Z2, Z3. And if we switch the order of these two, three, and if we switch the order of these three, it doesn't matter. We will still calculate the same result for each of the words inputs. So as to how to calculate the Z1, Z2, Z3 vectors, and we can further illustrate this calculation process in the next pages instead. Okay, so given two inputs x1 and x2, which can denote in the words we mentioned before, like these two words x1, x2, x3. Of course, here to simplify the representation, we just show you with two words. It is very easy to extend this one to like multiple words as inputs, right? And here we assume we have two inputs x1 and x2 as the input vectors. And the order doesn't matter. They can be in any orders or inside the input sentence. So inside the transform model, we define some intermediate like variables like q1, q2, k1, k2, v1, v2. And this name of this vector doesn't matter. Normally we call them as query, key, and value vectors. You can ignore these names. It doesn't matter actually. And you can just say them as a q vector for x1, k vector for x1, v vector for x1. Similar for this one for the x2. And you may wonder how can we define these three vectors, q, k, v, three vectors. We can define q, k, v based on these x1 and x2 vectors respectively. So given this x inputs, we can define a following connection layer, the one layer multi-layer perception, parameterized by the W as shown here. It's W denoting the weights incorporated in the following connection layer, right? So by utilizing this W vector as a weight, we can define we can calculate the q1 vector of this x1. This q1 equals to what? This q1 will be equal to the by times this one with this matrix. We can generate one vector of length 3, right, as shown here. Similar for the q2. It's for the q vectors. And this is a variable for calculation of these q vectors. We also name this one as wq, q denoting this for the q vectors. So besides the variable for the q vectors, we also define the variable for calculating the k vector and the v vector as well, which are denoted by the wk and the wv as shown here. So the calculation process is very similar. So by multiplying the variable matrix with this x as the input, then we can define the qkv, these vectors. So these are the intermediate terms we will use in the following part for calculating the self-attention scores, and we further utilize them to define the z vectors as shown before. Okay, so you just need to remember, for this x input, we define three terms, qkv, these vectors, by utilizing the variable as shown here. Then we wonder how can we utilize these terms to define the attention scores. The attention score actually is very straightforward. So remember, given the inputs x1, x2, we can define the three terms, qkv vectors for them, right? And then we try to learn the representation for the x1, x2 as z1 and z2. And you may wonder how can we calculate z1 and z2. And we can take this one, x1 as the first one as an example, right? So we mentioned we have calculated the qkv, for the vector already. When we learn the representation for z1 and z2, we have to integrate information from this x1 and x2 together, right, for defining the representations. However, for learning the z1, these two will play a different weights or different roles in learning the representation, right? They have different weights. And we denote the weights as attention scores as shown in this page. How can we calculate the attention score? We know we have a q1 vector and a k1 vector already, right? So therefore, we can define one score as q1 vector times with k1. So we can define a score first as the inner product of the q1 times with k1. So by times them together with the inner product, we can calculate one value out, right? With like 112 as shown in example, as shown here, right? So when we learn the representation for z1, besides this x1 as the input, we can also capture some information from x2 as well, right? Because they are in the same sentence. So therefore, beside the first score, by times is q1 with k1, we also times is q1 with k2 as well. This term denoting how important this term, for the x2 is in the representation for the z1. So by times q1 with k2, we can also have a score as output, right? So this is a score we can calculate based on q1, k1, v1, and q2, k2, v2 vectors, right, for them respectively, right? And then furthermore, besides the score we define here, and we also rescale its scores by dividing scores by the dimension of its true vectors. Depending on the dimension of its QKV vectors, we divide these scores by the square root of the dimension. Let's assume if the dimension of this vector is 8, then we can divide this 112 by 8. Its result will be 14, right? Similar for this one is 19. It's 96 divided by 8. It will be equal to 12 as shown here. So these are scores we can calculate by dividing the score with this square root of the dimension for these QKV vectors. And you may wonder why we have to divide them by the square root of the dimension. The main purpose is to controlling the variance in the learning results. So by dividing scores with the dimension, the square root of the dimension, we can control the variance of this result to be in a certain range. So based on these two scores, we can further feed them as inputs to the softmax function, and we can normalize the score weights. Right, we have 14, we have 12 as shown here, and by normalize them with the softmax function, this one will be mapped to 0.88. And this one will be normalized to 0.12 instead. So in this way, we can show the summation of all the entries will be summed to 1, right? And they denoting the scores distribution between these two inputs. This one means that when we learn the representation for the first word like Z1, and the X1 actually plays a higher weight, right, than the second term. This one denoting the weight for capturing information from X1 in learn Z1. And this term denoting the weight for capturing information from X2 in learn Z1 actually. Then it comes to how can we define the Z1 vector. This Z1 vector equals to what? Equals to the weighted summation of V1 and V2. We can represent this Z1 as the weighted summation of V1 and V2, and the weight are denoted by the score we calculated here. So this Z1 will be equal to what? Equal to 0.88 times V1 plus 0.12 times V2. It's a weighted summation of V1, V2, and the number of weight is defined by the term we calculated here. Right, this is a way we can calculate Z1 as the representation for X1. It captures information from X1 or also X2 actually. However, these two will have different roles, have different weights in learning the Z1 representation. So in a similar way, we can also learn the representation for Z2 in a similar way, right? We can also calculate scores. However, here we have to change this Q1 to Q2 instead. And we can calculate the scores of different inputs, in learning the Z2 vector in a very similar way. We find that in learning the representation for the Z1, Z2, we have to integrate information from different parts, different inputs as shown here, and they will have different weights. And how are the weights? The weights are defined by themselves. We calculate the weights of these inputs, by themselves, by the QKV vector, right? This QKV is defined by the X1 and X2 as shown here, right? So by utilizing the information from themselves, we can define the weights for the summation and for learning the representation as a result. So given the X input, we can define the QKV vector for them respectively first, according to the variable as shown here, right? So this is very straightforward, right? And then furthermore, based on this QKV vector we defined in the previous page, we can further calculate some scores for the summation or for the integration of the information among them. When we learn the representation for Z1 for X1, we can integrate the information together. However, the integration weight is defined by themselves. We can first calculate the scores by utilizing the QK vectors, and we can further scale them and by dividing them by the square root of the dimension of these vectors, and further normalize them by the softmax function to define the weights, right? This will be the weight to be used for the summation for learning the representation of Z1 and Z2. Okay, so in this way, we can calculate the representation for the Z1, Z2 for the inputs X1 and X2, right? And this is for the individual inputs, and we can analyze them one by one. And when it comes to the data with multiple inputs, we can also simplify the calculation process by the formula as shown on the right-hand side. So given the inputs, we can organize all these vectors in the inputs together, because here we only have two, right? If we have more, we can define a similar matrix like X as shown here by stacking them to each other, right? This row denoting X1, this one denoting X2. If we have more inputs, then we can just put them below this two, right? Have this matrix X denoting the inputs. Also, according to the previous page, we have these parameters for defining the QKV vectors, right? If we have multiple inputs, we can calculate these Q vectors together as a Q matrix as shown here. This row denoting the Q1, the second row denoting the Q2 vectors. However, we just simplify the representation by stacking them together into one matrix as shown here, right? Similarly, this K matrix covers K1 and K2, and V matrix covers V1 and V2. We also have a very complicated calculation for the score as shown here, right? Actually, the calculation process of these scores can be simplified as the formula as shown here. Given the QKV, this matrix covering all these vectors as shown here, we can denote the calculation scores in this part by the formula we should have on the right hand side. We mentioned here we have this inner product between Q and K, right? So therefore we can represent the QK, the scores for all the pairwise in the inputs as Q matrix times the K matrix transpose. We also mentioned here we have the rescaling of these scores by dividing the scores with the square root of dk, right? We will incorporate here, and we have a softmax for the normalization. And this result will be a matrix. It covers pairwise attention scores for each inputs. It covers all the scores like 0.88, 0.12, and so forth. All the scores will be stored in the results as shown by this term. We further mentioned that we can utilize the scores as well as these V vectors to define Z as the embedding results, right? So therefore, by integrating these attention scores together with this V matrix, we can define the learning results of these inputs as this Z matrix. We can denote Z equals to the softmax. Inside we have QK transpose, we have this rescaling and softmax normalization, and we can further times it with this V matrix as shown here. Then we can define this result to be Z. This Z covers Z1 and Z2 as a result. And on the right hand side, we just provide this linear algebra, this representation of this calculation process into one single formula as shown by this one. So according to this formula we show here, we can calculate the embedding results by the inputs into this Z matrix, right? So by utilizing this formula, we can define the Z matrix output for this input X as shown here, right? And in this way, we can embed this input X into this Z embedding vectors, right? Okay, so this is a self-attention score used in the transformer. I hope you can follow me for this part. And later we will use the attention mechanism in building the transform models.